Hi everyone, welcome to the Raith training video. This video should supplement your in-person training and is not a substitute for the in-person training. Consider this video a demonstration of the basics in terms of alignment procedures, calibration, and overall use of this tool. I'm going to pattern contacts to a flake of non-continuous film, but this is just one of many scenarios in which electron beam lithography is useful. So please see the Raith guide or lab staff for assistance specific to your patterning needs. First, log in to the Raith using the lab access computer. Go to the metrology section and click on the Raith and activate. Then log out of the lab access computer. Hey everyone, my name's Mike Rotter. I'm a graduate student here at UT Austin, and today I'm going to be talking to you about using our Raith E-line Plus EBL lithography tool. So the lithography tool is located in the metrology bay. You can see it here. It's located in the same room as this Zeiss SEM tool as well. So with two tools being in the room used at the same time, it can possibly get crowded. So we ask that you only bring in the necessary supplies that you need to do your patterning or imaging, and this can include your wafer piece, tweezers, lab notebook, pen, USB. But if you have a large tote box or a lot of other wafer pieces or supplies that you're not using, then please leave those outside the room. Additionally, you'll want to grab one tech wipe because when we mount our sample on the sample holder, we'll place the sample holder on the tech wipe. So the sample holder is located inside this load lock chamber, and the load lock chamber is vented in its standby mode. So you don't need to vent the load lock chamber to remove the sample holder. All you need to do is to open the load lock door. So that's what I'm doing right here. And then I'm just going to open up the load lock chamber. I touch the door. I don't touch the transfer rod when I'm opening the door, just so my gloved hand doesn't touch the transfer rod. And I'm just going to take the sample holder, and as I mentioned, I'm going to place it on the tech wipe. Here I just showing you the sensitive areas of the back of the sample holder. These three places are where the ceramic balls from the stage touch the sample holder, so we want to keep those free of dust and particles. So that's why we place the sample holder onto this tech wipe here. And I place it in this particular position here, shown here, and that's because you see that this direction I'm pointing here is the positive X direction, and this direction here is the positive Y direction. So when I'm imaging, part of my sample, if I mount it like so in this position, the features will appear upright. Looking at this sample holder, you can see there's one clip here that you can use to mount small circular wafer pieces, and also there's these clips here that you can use to mount 1 or 2 inch square samples or centimeter squared samples. And it's important that you clip your sample in properly and securely so that the electrons can have a grounding path, otherwise you'll get some charging. The Faraday cup is located here. I'm pointing at it with my tweezer. It's just a small black dot. You can barely see it, but that's where it's located. And I tend to mount my samples as close as possible to the Faraday cup. So if I ever steer from the sample to the Faraday cup or Faraday cup back to the sample, I don't have to steer for too long. So here I'm just going to mount my sample onto the sample holder. So all you need to do is just place the sample in and push on the clip and just make sure it's clipped in. And it doesn't have to be at a precise 90-degree angle. You can be off by a few degrees. You could be off by 45 degrees. The softwares allow for some angle adjustments. So yeah, the placement of the sample is not critical, but I do tap on the sides of the sample here just to make sure it's securely clipped so I don't get any charging. And then I'm just going to take the sample holder and place it onto the transfer rod. You can see I'm doing that here. There's 2 trenches on the sample holder that I'm pointing at, and then 1 hole there. And this is pretty self-explanatory, but the rods here are going to sit within the trenches, and then there's a metal spike, a tooth-like piece of metal that's going to fit into the hole. So yeah, you just mount the sample holder onto this transfer rod. There's no, you really can't mount it in any incorrect way. There's really only one way to mount it. So once it's mounted in, I'm just going to close the load lock door and we can get started bringing our sample into the main chamber. So the first thing to do in terms of the software is to just open up the eLINE Plus software. And so all you need to do is just click on the icon here, and you'll be prompted to enter a username and password that Rico will give you once you get authorized to use the tool. And you'll just enter your username and password and the software will be brought up. Now each user has their own individual settings and their own individual workspace. So here's the software being brought up, and we can go to the load lock tab here to bring in the sample. We're going to bring in the sample via the load lock, so we're going to go to this particular load sample icon and click OK. We're going to load it in. So it just asks you here, it prompts you to make sure that there's no samples already in the sample in the main chamber. And now instructions to bring in the sample are going to appear. So the first one is to close the load lock door. We already did that, so we press OK. Now the tool is going to pump down the load lock chamber, and once it's done that, more instructions will appear. So we're going to open the load lock valve and we're going to insert the transfer rod. So here you can see I'm going to pull up on this knob here, this release knob, and then I'm going to turn the load lock valve from lock to open, and I'm just going to pull it out slowly. Like you see here, don't pull it out too hard. These are mechanical pieces, so eventually they wear down. And then I'm just going to press in the transfer rod like so. So you want to press it in all the way until you don't see any more of the shiny metal of the transfer rod. And so I just kind of press it once to make sure. And then I just press OK on the instructions. So the next thing that happens is the stage is going to raise from a stage height of 1 millimeter to 16 millimeters. So you can see in the bottom right hand of the screen the coordinates. You can see that the Z direction of the stage is moving right now, so that there's a green light on the Z direction, and you can see right here that the coordinate is increasing in the Z. So it started at 1 and it's going to increase to 16. And this is the longest part of the load sequence here, just waiting for the stage to go up to 16. And you can't really edit the files or anything while this is happening, so generally you just wait, or you can prepare your notes, or uh, talk to your friend or something like that. So you can see in the coordinates there's an X, Y, and Z. Those are stage coordinates. And then there's a U, V, and W. U and V are user-defined coordinates. They're vector combinations of X and Y that allow you to steer around your sample in a parallel and perpendicular manner, even if your sample is not perfectly in line with the X and Y of the stage. And the W will become the working distance of your sample, but you'll need to adjust the working distance first. In a sense, you'll need to set the working distance before you can steer in W. So it's almost to 16. It's got a few more millimeters to go. And yeah, just a reminder one more time, the W needs to be adjusted to be the working distance. So before you adjust it, it's a meaningless number. Luckily, if you use the same sample height each time, then you don't need to adjust the working distance or the W each time you use the tool. That number will be saved. That adjustment will be saved after you use your account one time. So you don't need to adjust W every time. So it looks like it's almost reaching 16, and when it does, more instructions will pop up on the screen. Those instructions are going to ask you to remove the transfer rod and then close back up the load lock valve. So that's what I'm going to do right here. The load lock chamber is vented and it's standby, as I mentioned earlier, so that's why we'll want to close the valve again. So here you can see I'm going to just pull out the transfer rod. Alright, and I've pulled it out. And then I'm just going to close the load lock valve. So the way I do this is you just push it back in, kind of in its same open position that you pulled it out, and then you just bring it to its locked position. Make sure it's all the way up, and then you're good. And you can press OK on these instructions, and more prompts will come up. So it'll ask if you want to reset the coordinates, and in general you'll press yes to this. It'll bring up a sample name, a place you can label your sample, so you can label it with your name or the sample that you're working with. There's an electronic logbook that's on this tool, so you can use it to manage your samples. Then it asks if you want to reactivate the last used column parameters, and you say, I say no to that. That's what the Raith people have suggested that we do. So here's the logbook I was talking to you about. So you can see what layers you've patterned. You can see some beam calibrations, right field alignments. If you label your samples, you can go back and see them. You can see a few of my friends here on the logbook have used the tool. So it can be helpful if you ever want to check back to see what you've already patterned and things. So the next thing I'm going to do is just open the patterning file. So I go to the Designs tab, which I call the Shapes tab, and I click the Open Folder. And each user has a folder that's designated for them. You can store your GDS files in. So here I'm just looking to find what GDS file I want to use to pattern. So, I'm pasting it in from my flash drive. So you can use your USB drive. You can insert it into the computer to access your GDS files. So, here I just pasted one into my folder, and I'm going to open it up here. So if I double click on it, I'm going to go into the viewer mode. The viewer mode doesn't allow you to edit your GDS file. So you can see if I try to click on something like this cross, I can't edit it. But if I click on the file and press edit, now I'm in editor mode, and I can edit any of the shapes or any of the layers that I want. Here I just deleted a cross, but you can add shapes, you can delete them. You can write your whole pattern on this software if you want to. Here I'm just clicking on the Layers tab. So this will bring up this Layers prompt, and you can click on the various layers to display them or not. There, I clicked off of layer 11 and 10, and you can see more of the pattern here. Now you can see these dashed boxes here. Those are the right fields. Alright, so again, I'm just pressing on some layers. You can just view your file to make sure everything's okay. Now, this is probably an odd looking pattern file for people that do traditional EBL, but a lot of people here do these single device patterns with contact pads like this. So it's a pretty popular thing to do with exfoliated 2D materials. So that's what's being shown right here. It's a very basic pattern. So I need to define first a working area. A working area is the area that I want to pattern. So I want to pattern everything in here, these contact pads and the probes. So I need to make sure that my working area surrounds everything that I want to pattern. So, in this viewer or editor mode, you can see at the top left, you can see some UV coordinates. And in this working area tab, I'm just going to enter in. Here I'm using a center position and then a size, and I can enter that in, click save, and you can see this gray box appears. So you can see the gray box is separated into right fields. Right fields are the amount of pattern that the E-beam will write before the stage moves. So in my particular case, and in these single device cases, oftentimes you just want to write the pattern all in one right field. So I call that a single right field working area. So we'll adjust for that later. But as I mentioned, if you have multiple right fields, the E-beam is going to pattern the pattern in the first right field and then steer to the next right field and pattern anything in that next right field. So one nice property of this Raith software is that you can define different Raith field sizes. So, for instance, you could do a traditional 100 micron by 100 micron, 200 micron by 200 micron Raith field, or you can do something large like 1,000 or 2,000 microns, something like that, on the order of. And as mentioned in the Raith guide, you want to make sure that the magnification times the Raith field equals 130,000 if you do create new Raith fields. So here I'm just showing, what you can see is that if I were to pattern this particular device with multiple Raith fields, the contact pads are split between two Raith fields. And I'm working with larger features. In this example here, we're just using the EBL mainly because this is a custom mask file only used for this single flake of material. So my features are still in the microns. So what you can see here is that I've just set the Raith field to just be the same size as the working area, 1,000 microns by 1,000 microns length. So the dashed box is now the same size as the gray working area box. And that way I'm not going to get any stitching errors. But if you are doing finer features or more traditional EBL, you may want to break your pattern up into 100 micron by 100 micron Raith fields because the smaller the Raith field, the less distortion you'll get from the beam going off axis. It stays closer to the center axis. So you also see these three red boxes kind of towards the center of the pattern. Those are the three layer 63 boxes that I'm going to use to calibrate the beam in a later step. So that's what those three boxes are. So yeah, I'm done doing that. Here I'm going to pull up a dose testing file and show you a file where I would split the working area into multiple Raith fields just because the total area of the pattern is too large to write in one single Raith field. So here's a dose pattern that I sometimes use on this tool. And if I set the Raith fields to 200 by 200 microns, you can see it'll just pattern each one of these sections at a time. And I wouldn't want to pattern this all in one Raith field. So you can pattern your features all in one Raith field if you want, but you're likely to get distortions in the pattern the larger the Raith field gets. And also sometimes the overall pattern is obviously too large for a single Raith field. But for many of the cases with these single device patterns like the one I'm going to be using in this example, here this 1,000 by 1,000 micron Raith field works fine. So here I've just set it, I'm just checking the working area. Alright, the next thing I'm doing here is I'm going to bring up the sample holder map. So it's just the one under here called USH, and I can just bring up this sample holder map. This allows me to steer around the sample holder. If I just press Control right click anywhere on the sample holder, I can steer to the sample. So this certainly helps me navigate to find my samples. So here's an image of the SmartSum software. This is the other program that's running besides the eLINE Plus software. Here you can see the EHT. I'm going to set that. Generally, people use either 20 kV or 30 kV to pattern. 30 kV is the maximum height, EHT that this tool will go to. So 20K is pretty normal. And so that's what I'm going to use. So you just double click on the EHT, just make sure it's 20 or set it as 20. And then you just come over to the bottom right here and you click and turn the EHT on. And you'll see it's running up kind of in the center bottom of the screen. Just wait till it runs up to its full value before you do anything else. So yep, now it's ramped up to 20 kb. You can see on this SmartSum software, you can select apertures, scanning, you can switch detectors. This is the same software that's used on the Zeiss. So please see the Zeiss video and get trained on the Zeiss before you use this tool. I'm not going to cover too much about the scanning and things like that, but everybody has their own scan settings that they like to use, various averagings, and etc. Okay, so here I just did a control right click and I'm going to steer to my sample. I generally steer to the clip because if I image my sample in the clip area, I'll expose some of the resist there, but your important patterns that you're going to pattern shouldn't be close to the clip. And you can see here I'm highlighting that when you move in the X and Y, the X and Y lights in the coordinate system down at the bottom right will light up green. So you can see they're lighting up green here when I move back and forth. So if I click on this button, I can bring up some crosshairs. I like to bring these up so I can see exactly where my position is that I'm steering. And there's also various other buttons up on the SmartSum software that you can click on and use that are useful. So this one, for instance, will tell me the brightness and contrast percentages of whatever aperture I'm using. So here's the button to unblank the beam. So you need to unblank the beam when you want to image your sample. Here's the joystick that can be used to steer around your sample. So you need to activate the X and Y like I just did. And now you can steer around your sample. So here at the right, you can see the clip, and then you can see my sample kind of out of focus here. Now, right now we're just imaging at a generic working distance. We have a stage height of 16. So what we're going to do here is we're just going to focus on the sample at that stage height of 16. So yeah, I'm just going to steer around to some sort of particle or any sort of shape that's recognizable on my sample. And just zoom in. Focus a little bit. Okay, so you can see my working distance is, you can see my working distance at the bottom, kind of in this toolbar here. And here I'm focusing on the sample surface. You can see a couple of alignment marks as well as some dust. Now you'll notice these alignment marks are pretty poor alignment marks. They're just made from photolithography, and the photolithography obviously wasn't great. But one of the advantages of this tool is the ability to do manual alignment and work with non-ideal alignment marks. So you'll kind of get to see that during this demonstration. So okay, here I am, I'm focused, so now I have an accurate working distance. You can see it's about 17.5 millimeters. So the working distance when the Z height, the Z stage height is 16, the working distance is about 17.4, 17.5 for this particular sample height. So if you have a different sample height, then your working distance will be slightly different for the Z equals 16 height. Now what we're going to do is we're going to adjust the W. As I was mentioning earlier, we need to calibrate the working distance. So we just go to this Adjust W in the X and Y tab. We unclick Read from CCD Control, and then we're going to click the droplet button here and read in the working distance that we have. And you need to make sure to press Adjust so that the working distance gets adjusted. So now you can see that for a stage height of 16, the working distance is 17.446. So now that W value is accurate, and we can steer in working distance, and we don't have to steer in height, we can steer in working distance. So the prescribed working distance for this tool is 10 millimeters. So if I want to go now to a working distance of 10 millimeters as opposed to 17.5, I can just type in a value of 10 millimeters into this W tab right here. So this is a way that you can steer in, again, you can steer in working distance as opposed to steering in stage height. So, okay, here you can see I finally typed it in. I typed in 10 millimeters. You've got to ensure that the length here is in millimeters. If you type in 10 microns, the sample holder is going to hit the last magnetic lens. It's going to hit the cone, and that's not going to be good. You want to make sure your base is UV. You can see I just switched it to X and Y, and if you do that, you're just going to steer in stage height Z. And then you want to just make sure that the position here is absolute. So there's no such thing as relative working distance. So we want absolute. So once we make sure the length is microns, the base is UV, and the position is absolute, we can press start, and we can start moving the stage. Now when you're moving the stage in Z, please go to the camera mode like I've done here on the SmartSem software, so that you can monitor the position of the sample holder relative to the cone, to that last magnetic lens. So here I'm just showing that you can kind of see. You can see that the stage is now rising. Now we're at a working distance of 17 and a half, and we want to go to a working distance of 10. So the stage is going to raise about 7.5 millimeters relative to what its position already was. So that's what's happening now. You can kind of see it raises. But as you noticed during the load, the stage rises relatively slowly. But that's good, because then you can make sure that you're nowhere near close to hitting the cone. Alright, so you can see it's kind of moving up. It's rising slowly. Alright, so now you can see that the Z height's 23, about 23 and a half. So we've reached our working distance destination, so we can remove that value from the W. And here's the unblank button. So if we want to image the sample again at this working distance, we could unblank the beam and image again. So we're going to use this secondary electron detector to image. And we're at a working distance of 10 now, so we can click on this toolbar and set the working distance to 10. This tool, you can't, from my understanding, track the Z value. So that's why we just manually enter in 10 after we've raised the stage. And you can see the sample gets in a little bit better focus, and we can image this alignment mark. Now again, this let's see. All right, so we can set an origin, which is something I always like to do. You can look in the bottom right here in this coordinates, and what this has done is set this particular stage coordinate x and y as the 0, 0 UV coordinate. Now in this video I'm not going to talk too much about UV coordinates. I go into detail about them in the manual that I wrote for this tool. So please read the manual if you're unclear about UV coordinates. So I'm going to select an aperture of 60 microns to use. This is the aperture that I'm going to use to pattern with. So here I switch to it. I'm adjusting the brightness and contrast because the current's different for each aperture, so we're going to have to adjust the brightness and contrast when we switch apertures. So here you can see the keyboard for this tool and is the same as the Zeiss. So we have magnification, focus, and the various other knobs that we can use. Here I'm changing the scan speed and doing some focusing, so we can, focus. When you do EBL, obviously you need a small circular beam. You want a smallest beam spot as possible. So you're going to do the same imaging type techniques that you would do on an SEM. You're gonna adjust the wobble and the stigmation and focus. So I'm gonna just find a feature on my sample that I can use to do all of that image calibration, or that the beam column calibration. Alright, so I'm going to reduce the scanning size of my box so that I can get a faster refresh rate. I can scan faster. I generally scan with a scan speed of 1 when I'm just imaging the pattern when I'm not focusing or adjusting stigmation. If I'm focusing, if I'm doing some precise focusing, I might slow the scan speed down some. So here I'm just focusing on this feature of my sample. Alright, so I'm kind of adjusting the brightness and contrast. And again, if depending on your feature size of your patterning, you can pay closer attention to the wobble and the stigmation and focus. The finer your features get, the more important it is to have that small beam spot. So here I am just adjusting the aperture alignment by doing the wobble. So again, if I click on some of these upper icons on the Smart SEM, I can display the percentages of the aperture align in the X and Y direction. So for the wobble, depending on how precise you want it to be, you can adjust the amplitude, but around the 20 to 40% is generally what I use. And as I mentioned in the SEM video, the idea here is to get an image that's not moving in the up and down or left and right direction, translational direction. So we want it to just go in and out of focus but stay in the same place. Alright, so here I am just kind of adjusting the wobble using these knobs, the same way that you do with the Zeiss. Alright, so I'm just adjusting the wobble here. And again, if you haven't been trained on the Zeiss, then you need to get trained on the SEM first before you use this tool, because as you can see, all the things that you learn how to do on the Zeiss, you'll need to know for this tool. So I'm adjusting the wobble still. If it's moving up and down, you'll want to move the X alignment and left and right the Y alignment. So it's backwards from what you'd think. Alright, so I finished with the wobble. And I can adjust the stigmation. Here's the two stigmator knobs that I can use to adjust the stigmation with. X and Y, you can see that. Alright, so again, if I click on this button, I can see the percentages for the stigmation, the X and Y. I can also click on the stigmation button here, and that will display the percentages as well. So I'm just going to adjust the stigmation. Okay, so yeah, I'm just adjusting this to try to get the feature to be as in focus evenly in the X and Y direction as possible. And this is discussed more detail in the Raith guide. Okay, so after tuning the stigmation, we'll refocus, and we can switch back from tuning the stigmation and focusing back and forth until we get an image that we're satisfied with. Again, my features are in the micron range, so here I have a particle that I'm imaging that's in the micron range. If you're going to pattern things that are in the 100 nanometer range or something, you'll probably want to get a good image on something that's similar to the size that you're going to be, of features that you're going to be patterning with. So the focusing will be more important the smaller your features are. Because here I'm still just adjusting the focus and stuff. I'm playing around with the stigmation. As you all probably know, you can kind of get the stigmation really out of tune and then tune it back to what's acceptable. Sometimes you have to get it out of focus or out of stigmation first before you get it to look good. Oh, I guess I'm checking the wobble one more time just to show you guys. So I think it looks okay. It's good enough probably for what I'm going to be patterning, which by traditional EBL standards is a quite large feature. Okay, so now we go to this Patternings tab and we open up the Beam Current tab, and we can steer to the Faraday cup to measure the beam current of our aperture. So I'm just going to steer to this USHF cup 2017. Here you can see we can either click to drive back to where we were before we measured or uncheck it. I always uncheck the box because after I measure the current using the Faraday cup, I always zoom out to make sure I'm directly over the Faraday cup. And so if you see, I just clicked measured and now I'm steering to the Faraday cup. So we've arrived at the Faraday cup and it measures the current at about 1.5 nanoamps for the 60 micron aperture. So you can record 2 currents at a time. If you measure more than 2 apertures, then you'll need to write the currents down in your notebook for the 3rd aperture. And you can see I press the back button here. If I press the back button, I'll steer back to exactly where I came from, and I just pressed the forward arrow. I can drive back to the Faraday cup. So you can use these back and forward arrows if you want to get back to a place you had just been. So here I'm zooming out and you can see I'm imaging the Faraday cup. So I always do this just to make sure that I'm right over the cup and that my current's accurate. So if you decide that you want to just steer to the cup itself, using the joystick or something, or the sample map, make sure, as you can see, I switched it to current position. If you're going to measure another aperture and you're already at the Faraday cup, you can just select current position here and the stage won't move. It'll just measure the current directly in that position. So next we can do an angle correction. You can see I was clicking on the angle correction tab. For this particular correction, you're going to need 2 points, like alignment marks, that have the same Y value. Or if you have a wafer with a nice edge to it, you can use that. But you'll want to adjust this angle correction so that you can steer in the UV coordinates. The UV coordinates are essentially the X and Y of your wafer piece, whereas the stage coordinate X and Y are the X and Y of the stage itself. So again, if you're still unsure about what the UV coordinates are, just go look in the Raith guide and there's a detailed explanation. So what we're going to end up doing here on the sample is picking one alignment mark that has a particular Y value. It doesn't matter what the Y value is. And then we'll choose another point. Now the angle correction is a vector. P1 is to the left and P2 is to the right. So you do want to make sure that your P1 is to the left of P2. When you assign those. Otherwise, it'll write the pattern reflected. In other words, the angle correction will be flipped. The vector will be in the opposite direction. So here you can see I'm just steering around the stage, finding my points. And You can see that when I was using the joystick, it's always good to just do slight steering motions and not really hit the joystick or be aggressive with it, because yeah, it's a mechanical part, so it can wear down. Alright, so I'm just going to kind of hone in on this first alignment mark right here, try to find the center of it. And I'm going to select this as P2. So I'm at the right side of my sample, so that's going to be my P2, and then I'm going to steer to the left side of my sample right here and select a alignment mark that has the same Y value. Now if you don't have alignment marks that are at the same Y value, but you do have alignment marks and you want to correct the UV angle, you can use the 3 points method that I showed a little bit earlier, and that's also discussed in the guide. So here I set the two coordinates P1 and P2, and then you need to make sure you press adjust like I did to adjust the angle correction. Alright, so now I'm just going to steer closer to where I want to pattern. So I want to pattern this. I have a grid of alignment marks here during this demo. So I'm steering to some alignment marks here. They have some big and small numbers. This, at the time of this recording, this particular alignment mark matrices pattern is quite popular in MER, so a number of people will use this mask, but I'm just steering close to my where I want to pattern, so that when I do start patterning, the stage doesn't have to travel as far. So here I'm just showing I'm going to steer again. To the correct big number. You can see that big number there. So this mask may not pertain to your particular patterns or wafer or substrate, but at least I'm just demonstrating that you can steer around your sample freely. So we can also adjust the origin again to set this as our 0, 0 point. And here I'm steering using the absolute position. So here I adjusted the origin again to 0, 0, and then I'm going to steer according to that origin. Now you can also switch to relative position and just steer relatively to every point you're on. So that's another method. There, I'm just going to steer a little bit closer to my sample. And you can see this alignment mark's been somewhat etched away, but I'm still able to use it if I wanted to do some alignment using this marker, where with some other EBL tools this this alignment mark may be no good for scanning. So I just switched to my 60 micron aperture, which is the aperture I want to pattern with. I was steering around with a 30 micron aperture to reduce the amount of effect that the exposure had on my resist when I was imaging and driving around. So I adjusted this particular coordinate to be 0, 0. It's important that when you're ready to pattern, before you start, that you correlate one of the positions on your GDS file with a stage coordinate that should correspond to that coordinate of the GDS file. So in this case, I'm adjusting one of the alignment marks that's set to the 0, 0 position of my GDS file as the UNV 0, 0 for this stage coordinate here. That way the software understands that this stage position corresponds to that position in your GDS file. So here I choose that correlation to be the 0, 0, the origin of my GDS file, but you can select other points as well in your GDS file. It doesn't have to be 0, 0. So also, I'm going to mention that in this basic demo I'm doing, I'm just using some manual alignment with alignment marks that I already have on my sample. But you can see in these tabs I'm opening up, you can also align, you can also do some beam calibration and alignment. If you don't have alignment markers, and you only have like a dust particle, or you can do automatic alignment with alignment marks. So there's different ways to do the beam calibration, the deflection calibration. So I'm just doing one of them here, but there's others, and it's laid out more detailed in the Raith guide. So here I just set the right field to 1000 by 1000 microns that we talked about earlier. I checked my pattern a few times to make sure that the layers I want to pattern, I know what layers they are. Now I just opened a new position list. That's the box that I brought up here. And what you're going to do is just drag your file in to the position list box. So that's what I just did, and then it pops up and it asks you what layers you want to scan. So I'm scanning the layer 63 layer. That's the layer for manual alignment with alignment marks. I just checked the working area. You will always want to click on this positions tab. So the position should be the center of your first right field. Now in my case, I only have one right field, so it should also be the center of my working area as well. And then you can click on the patterning parameter tab, calculator, and you can enter the beam current, or if you've only measured one, it should automatically be there. And you can choose the step sizes in the X and Y and the dose. So what you do is you'll enter the beam current, step size in X and Y, and the dose, and then calculate the dwell time. So I've clicked equal steps in the X and Y, so that I have equal dwelling in both X and Y. You can see I changed the step size here, and then I calculated the dwell time. So the last thing to check is to just make sure that the beam speed's not too large. If you're patterning really fine features, you may want to keep the beam speed below 5 or below 10. Larger features, it's not as important. Or in contact pads and things, you can keep the beam speed quite high, maybe around 20 to 40. So again, in order to have brought up that calculator and in order to have brought up that calculator and the setting the working area and the position, etc., you just right click on one instruction on the position list and just go to properties. So I don't think I had mentioned that. You just right click and go to properties to bring up that calculator. So here I'm just checking the kind of, I guess, the size of my features. You can see this is a pretty odd looking mask file, and that's because I'm working with an exfoliated flake, so there's other material around my flake that I don't want to lay the metal on top of, so the lines are kind of looking all over the place. So here when I'm ready to do my alignment in layer 63, you can just see I pressed right click and then scan. Now it's going to scan these image boxes that I had in my GDS file around these 3 alignment marks. So here's the first alignment mark. So a cross will pop up, but it won't quite be in the center of my alignment mark. So I'm going to click Control and then left click and drag to the alignment mark. And it's going to do this for all 3 of the marks. So I'm going to just click Control, right click and drag, and I drag the cross into the center of the alignment mark. So this is a very popular way of doing alignment, especially in this tool, because even though it's not very efficient, obviously, a lot of times, you might only be patterning 1 or 2 devices, and you might want to just do some manual alignment if you don't have precise alignment marks and things like that. So it's a useful technique. But you can, of course, on this tool do automatic alignment for many devices, and you don't need marks per se to adjust the beam deflection So those techniques are discussed in the manual, in the Raith guide. So I'm going to scan one more time. It made the adjustments. So you can see here that, now the crosses are pretty close to the center, visually at least, in the center of the alignment marks. So I'm just double checking. You can go through it one more time to make sure that it's scanned properly. Adjusted properly. And you can see the zoom's pretty close to 1, and there'll be some shift and rotation of the deflection that's accounted for. So, but you can see that this method of alignment is really geared towards writing a single device or a few devices. But you can do some automatic alignment if you're going to write like an array of devices or other different, more traditional like EBL patterns. This demo is basically kind of the most simplistic things you can do on this tool. So the next thing I did was just select what layer I wanted to pattern, and in this patterning parameters tab, you can see I clicked this times button, and it'll give you an estimation of how long the write's going to take. So you always want to make sure that your write's not going to be longer than your reservation. And then all I did here was just go down when I'm ready to scan my layer. I'm satisfied with my alignment. I can just right click on the position list instruction and just press scan, and you can see I just scanned, and we fast forwarded through the write time itself. It wasn't that short. It was around 12 minutes or so, but we just fast forward. So the write finished, and now I'm just going to steer away from this particular sample, from this particular device, sorry. We're going to stay on the same sample. I think we're going to do one more device. So in order to get back to imaging, you can see I just clicked on the patterning/image tab. You want to click on that so you can get back and activate the SmartSem software. So I unblanked the beam here. I just wanted to double check that I was in the right position, so that's all I was doing. Normally after a write, I'll always steer to some coordinate that I know about, that I don't care about exposing, and I'll just unblank and make sure that I'm in the position that I expect to be. Okay, so I'm just going to select a second patterning file and double check it to make sure it's what I expect. I'm going to define my working area the same way I did before. It's the same working area and size and sample. I'm going to click save on that, and you can see it kind of zooms in. Here's my pattern. It looks pretty weird. Cool. And I can, steer. I'm going to steer to a new position on the substrate because this second device is in a different location. Alright, so I'm steering around. You can see that the U and V coordinates have moved. And the X and Y, obviously, because the stage has moved. Alright, so I'm in my new position here. I'm just going to steer a little bit closer to where my sample is. Sorry, where I want a pattern is. So I end up steering pretty close to where I'm going to end up patterning. That way I can just make sure that the stage is close by already to where I want to pattern. It doesn't have to move very far. Alright, so I'm just finding the alignment mark that I want to be at. And I can switch to my 60 micron aperture that I'm going to pattern with. Again, I was just steering around with a 30 micron aperture to reduce the effect of the exposure of the beam on the resist and the various other places of the sample. So here I'm going to set this particular UV as 0.2 millimeters in the U and 0.2 millimeters in the V. So this is different than last time. Last time I associated the stage coordinate with the 0, 0 position of our GDS file. And now this time I'm associating this stage coordinate that I'm at, this alignment mark, with the position 0.2 millimeters in my GDS file, or 200 microns in the U and 200 microns in the V in our GDS file. So you can associate any stage coordinate with any UV coordinate in the GDS file. You just need to make sure you have that association by adjusting the UV position of the stage coordinate that you're at. So I just set the right field again to 1000 by 1000. Going to drag in my file here and press 63. Right click and go to properties. Make sure my working area is correct. Click on the position tab. Go to the patterning parameters tab. Click on the calculator. check the beam current, adjust the step size to what I want. If you're doing finer features, I recommend the smallest right field sizes with the smallest step sizes. These step sizes are basically the distance between dwell points. And here I'm going to scan my pattern again. It's going to expose the image scan boxes, my layer 63 boxes that I have in the GDS file. So you'll notice that the first one didn't have an alignment mark. The box didn't. The alignment mark was actually etched away. So you can see I can adjust the beam deflection calibration using 2 of the 3 boxes, and I can click use only the corrected marks. And I can go back into my file and I can change the position of any of my layer 63 boxes in the editor mode. So you can see this one right here it's image scanning in the right place, but there's no alignment mark there because it was etched away. So I'm gonna select a different alignment mark that's up here, and I'm gonna move the box over there so I can calibrate using that alignment mark. So I just click on the box and I can just change its position. Alright, so now the box is in that alignment mark. I have a matrix of alignment marks, and it doesn't really matter which ones I use to calibrate the beam deflection. And again, that's what we're doing when we're doing these layer 63 alignment scans. We're calibrating the beam deflection. So now when I scan my layer 63 boxes, all the image scans will have an alignment mark within them, and I can calibrate using 3 alignment marks. And I'll do it one more time. And I just want to mention this calibration is different than the UV angle correction in a sense. The angle correction is so that you can that you calibrate your steering in the UV directions. So that's calibrating the stage steering. And then what we're doing here when we scan image scans like layer 63 or other type of alignment like that, when we do image scanning or line scanning, we're adjusting the beam deflection calibration. So that deals with, how the magnetic coils are deflecting the beam. Are they deflecting it the distance and the direction that you expect? So that needs some calibration as well. So you always want to do these type of calibrations before you start patterning to try to get your pattern to end up being as accurate as possible. So here I'm scanning the pattern. We fast forwarded it, but it took about 10 minutes or so. But that's all you do. Once you're ready, you just right click and press scan. Now you can always stop the scan if you've scanned something, you've realized it's in the wrong place or it's taking too long and you need to come back. You just press stop on the scan when you can see that box that'll pop up, or at least you saw it earlier, and you can just press stop on it. It'll cancel the scan. So here I'm just going to steer away from my area that I just patterned. I'm hesitant pressing the start button, it seems. I think I was originally going to pattern one more device. So here you can see that you got to click this image tab that I just did on the top of the Raith software, so you can activate the SmartSem software and image again. If you ever are trying to scan in the SmartSem and you're just seeing a black screen, it's gonna either be because your brightness and contrast are off, the beam's blanked, or that image tab is not clicked. So again, I just unblanked the beam here, and I just made sure that I was in the right position. So I'm all finished patterning. I'm just going to unload the sample. So I went back to this load lock tab, or this load and unload tab, and clicked unload the sample. And the instructions popped up just as before. So what's going to happen is that the high tension is going to turn off. The stage is going to go to 16 millimeters back from wherever you were for your working distance. It's going to go to a stage height of 16 millimeters. And then the load lock chamber is going to pump down, and we're going to insert the transfer rod here in the same manner that we did previously. So you can just you just saw me pull out the load lock valve and then insert the transfer rod. So the next thing that's going to happen is the stage is going to lower from 16 millimeters back to 1 millimeter, and you can see here the stage, the sample holder is has now been kind of laid down, if you will, on the transfer rod. So as the stage lowers and the transfer rod's in there, the sample holder will just be lowered onto the transfer rod. So here you can see now it's resting on the transfer rod, and you just pull it out. Now you can see inside the chamber where there's no sample holder. So here you can see what I'm doing. I'm just pulling out the transfer rod once the stage height's reached the Z height of 1. I'm pulling it out in the same way that I did to load the sample in. And then I'm just going to close back up the load lock valve so I can vent the load lock chamber and remove my sample from the sample holder. So I do this in the same way as discussed earlier. Click OK. And then it says that the unload procedure has been successful. And we can exit out of the E-line Plus Raith software, but please don't log out of the SmartSem software. That stays open all the time. So I'm going to let the load lock vent. It should only take a few seconds. It's already vented. So I open the load lock door, and I'm going to remove my sample here from the sample holder. Alright, and when you're finished with the sample holder, it's just stored inside the load lock chamber on the transfer rod. So just put it back onto the transfer rod, and then close the load lock and close the door. And you don't have to tighten the door too much, just enough. You don't need to over tighten it. And then, yeah, you'll just take all of your stuff with you when you're done. Now, the tech wipe, it doesn't have any chemicals or residue on it, so you don't need to throw it out. you can just put it at one of the solvent hoods like E05 or L10. They can be reused. They're kind of expensive, so they can be reused. They don't have, uh, chemicals or residues on them. So when you're all finished, you'll just log back into the lab access computer, go to the metrology section, and click on the Raith, put it in idle mode, and then you're logged out and you're all set.